Here is a quick run through of an example using the squeeze theorem. Let's see. Not sure how to flip through these things. Here's the squeeze theorem that says if f of x is a function that's less than or equal to another function g of x, which is less than or equal to yet another function h of x, when x is near a, except possibly at x equals a. And it turns out the function on the left, f of x, has a limit as x approaches a, and the function on the right, h of x, has a limit as x approaches a, and they're both equal to L. Then the function that's sandwiched in the middle, g of x, also has the same limit as x approaches a. Notice x is approaching the same value a in all of these. So now let's look at our funky example, wherever it is. Well, before the example, there's a picture that we like to look at is like the graph of g is sandwiched between the graph of h and f near x equals a. So near a, anyway, the graph of g is sandwiched between. Far away from a, other things might happen. Out here, g goes above the graph of h. So let's look at our example. We're going to find the limit, if it exists, of the limit as x approaches 0 of the absolute value of x times sine of 1 over x. And the problem is that the product theorem for limits doesn't apply to this function because the limit of sine of 1 over x does not exist. So we just can't write this as the limit as x approaches 0 of the absolute value of x times the limit x approaches 0 of sine of 1 over x, because we're not allowed to write this, because when you look at the graph of the function, the graph of sine of 1 over x doesn't settle in at a value as x approaches 0 from either side. And so in fact, neither of the one-sided limits from the right or the left of sine of 1 over x exists. So we might suspect that no limit exists, but when we look at it, we can use the squeeze theorem and see that the limit does exist. So how do we do that? Well, first of all, we're going to recognize that when x is approaching 0, it's not 0, and for those values, the sine of any angle doesn't matter that it's 1 over x. The sine is going to be between -1 and 1. So if we look at the absolute value of x being greater or equal to 0, we can just multiply this entire inequality on all sides by the absolute value of x without changing the direction of the inequality signs. And we get this compound inequality. The negative absolute value of x is less than or equal to the absolute value of x times the sine of 1 over x, which is less than or equal to the absolute value of x. So if we take the limit as x approaches 0 and apply the squeeze theorem, and this is where we use the squeeze theorem, because the limit as x approaches 0 of the negative absolute value of x and the limit as x approaches 0 of the absolute value of x are the same thing, 0, we get that the bit sandwiched in the middle is going to have a limit as x approaches 0 also of 0. So in other words, the limit as x approaches 0 of the absolute value of x times the sine of 1 over x equals 0. So let's look at the graph to see why this is so. Just a real quick graph. Here's y equals the absolute value of x. The blue graph underneath is y equals the negative absolute value of x. And in between there's absolute value of x times sine of 1 over x, and you can see there's infinitely many waves in there. So remember that inequality we were looking at before, the sandwich part? Negative absolute value of x is less than or equal to the absolute value of x times the sine of 1 over x, which is less than or equal to the absolute value of x. And so what we're saying is this middle function is trapped between